Can you see the screen now?
Yes, sir.
Okay, so today the first lecture will discuss reflectivity method by Brian Kennett for layered medium. So this is built upon some of the concepts that I discussed last week, and let's get started on this. So here the goal is to do like full waveform inversion, full waveform modeling, and but for layered medium, okay, it's for 1D medium. So now you know what is 1D, what is 1.5. So this we're talking about 1.5D because layered medium with point source, okay. So this is going to be 1D medium, but with point source. So the medium is actually 3D and basically has cylindrical symmetry in terms of the structure. Excuse me. So what we will look into is a method that is based on rigorous solution to wave equation. And here,
Oh, okay.
any question? So here we will look at how we can solve the wave equation with special condition that the medium properties are varying only as a function of depth. Okay, and we will compute reflections like this. Okay, so we'll compute reflection and transmission plus some other interference effects, and we'll describe a method which will be able to handle an SR2P also. Okay, and this is definitely going to be computationally more expensive than a convolutional model, but still this is not really as expensive as doing a 3D finite difference or finite element. So this is doable. This is computationally not that expensive when it comes to layered media that is isotropic. When it's anisotropic, that actually adds a bit more to the cost. Okay. And remember, I'm talking about full wave modeling. That means I'm going to try to include everything. Okay. All kinds of wave effects. So let's try to just try it with some examples here. Sorry about this label here. So let's say that I have well logs of velocity, p wave, shear wave, and density logs. And what I want to do is to compute simply use this linearized Zopritz equation, which we talked about the other day. This is what is also known as AVO equation. Three term. There's an A, B, and C. This is called intercept. This is the slope, and this is the curvature. And if we just use the convolution model, this is one of the exercises I gave you last week. You'll see that the seismic traces look like this. And here there is no NMO, and this is basically in angle domain. Now, what has been done here is that for every angle, we compute reflection coefficients through each one of these interfaces, and then I just convolve with a wavelet. Okay, and here we have used the same wavelet for all angles. Okay, now that gives a beautiful picture, but how reliable is this? That is the question, and why do we even care to do full modeling when we're getting synthetics, which looks very realistic? However, you want to recall some of the assumptions that were made in here. And the first thing that we assume here is that this linearized reflection coefficient equation is valid. What it means is that our contrast in p wave velocity, it's called this alpha, shear wave velocity in beta, and the density rho, these are these are small in the sense that delta alpha over alpha is far, far less than 1, delta beta over beta is far, far less than 1, and delta rho over rho is far, far less than 1. So this is more or less smoothly varying medium and with some small perturbations. That is the assumption. And you can see from this log that which is not quite correct because there are some large contrasts if you go to regions like this. So that's where I think it becomes interesting. So what is the other issue here? Anybody? Of course, we're assuming that it's 1D. That's okay. So other assumption is that whenever you compute reflection coefficient at these interfaces, you are assuming that your model is actually simple layer over half space locally. So, or the layers are so thick that you're not seeing any response from any other layer interfering with it. Okay, so that's one other assumption. That means we're not well. Let me add something to that particular statement. We're assuming that the layers are thick enough that you can assume that this interface has no effect on the other interfaces have no effect on the reflection coefficient of this particular interface. Then you could ask me like, what? Why are you saying that? Because if I have a thin layer, then I'm actually taking the response of this, I'm taking the response of that, and these are interfering when I'm computing synthetic seismogram. Yes, that is true, but this one does not include any of the internal multiples. Okay, so that's one. That's one other thing. And third thing is that it does not include transmission coefficients. It's simply layer by layer reflection coefficients. Ideally, as I showed you last week, that if you have like two interfaces here, we have this. Let's say this is the primary. Now, if you look at the primary for the second layer, then sorry about the poor drawing. Here we have a transmission coefficient, then we have a reflection coefficient, then we have a transmission coefficient. But since we're assuming that the interfaces are sort of, they don't have large contrast, we are kind of ignoring the transmission coefficients. Okay, so that's definitely one other assumption. And then finally, another assumption is that, last but not least, is that this equation would always give you real numbers. But we know that when you have large contrasts, then you can have post-critical rays if you go to high angles, and that is where your reflection coefficients are complex, and that is not included in here. But then you can ask me why. You can ask me, okay, so how about not using this equation, but use Zoprist's equation, but you still convolution model? Well, that's a better equation, you can say. In that, you can still use convolution model. The only thing that is different here is that you are computing reflection coefficients in Zoprist's equation, and it will give you the complex numbers and the reflectivity and things like that. And of course, you have to modify your convolution because when it becomes complex, it's much easier to do this in frequency domain, just simply multiplication. But yeah, so that can give you slightly better picture depending on the layered structure that you have. But still, Zoprist, even with Zoprist, you still have this assumption that the interfaces are well isolated each time you compute the reflection coefficients, and it does not include transmission coefficients. It does not compute uh, compute the internal multiples. But whether you're using Zoprist or the linearized equation, 2-term or 3-term, you can still include transmission. It's only a matter of keeping track of it and then multiply up and down going transmission coefficients. But even then, you're not getting the full response. So we need to see how we can compute the full response, and then we compare it with these approximate methods and see if there is any usefulness of the full response. So to compute this, let's try to block the wells, and at different wavelengths. and then do Backus averaging in each one of these. So then let's try to see if this is if this convolutional synthetic model is valid. So we'll look into full waveform modeling. So we have these primaries, and then let's say that we have a lot of these layers. And then what you need to do here is to be able to take into account all of these reflections and transmissions all the way from going from top to the bottom or from bottom to the top. Okay. And here I'm just doing ray tracing. Okay. Just to demonstrate that, but this method that I'm going to talk about does not even require ray tracing. And the reason for that is that we'll go into tau p domain and or mega p domain, and I'll explain to you why we don't do a ray tracing in a mega p domain. So here is an example where this is the log has been blocked to 10 wavelengths. So here, this is your convolutional, but with Zupf's equation, and this is with wave equation. Okay. And here, this is the 2-term, and this is the 3-term. So if you compare those very carefully, what you see that for near angles, actually there is not a lot of difference because these are all pretty blocky layers, and the contrast is not that high. So, we have ignored the internal multiples. But if you go to high angles, you can see there are a lot of differences. So this shows you very clearly that if you want to include high angles, you cannot really use a convolution models. So again, I'm now blocking it into 5 wavelengths. So layers are finer, and you can see now the differences are becoming more and more pronounced. 2-term and 3-term is quite a bit different. These two sections are quite a bit different from what you get from exact Zopf's and from wave equation. Now, convolutional Zopf's is looking better, but still it's not matching your wave equation based. And I have not talked about what is the wave equation based method, which is the topic of this particular lecture. But for now, let's assume that we know what wave equation based method is in this particular case, and just for comparison. So just to set the motivation, and you can see that there are some differences at large angle, even with the exact Jones equation. So again, you block it finer, and you can start to see the differences coming out very strongly between convolution and the wave equation. So the details of the layering is not captured very well by either of these approximate methods. So the motivation for studying this method called reflectivity method, which was originally proposed by Fuchs and Muller, and it has been put into much more rigorous form by Brian Kennett in 1974, and then it has been extended to anisotropy by Fryer and Fraser, who were my advisors from a PhD. So this is the principal technique for computing exact synthetic seismograms in horizontally stratified, elastic, or an inelastic. It could be including the effect of Q is trivial in this particular method, and also you can include anisotropy. So unlike the ray-based method where you are picking each ray one ray at a time, this will give you complete wave field. And again, I have not explained to you what is a ray, and I will do that in the next lecture. But until then, just I assume that you all basically have the basic intuition about the ray, and this is something we grew up learning from optics, right? So here, this method includes primary reflection, P2S, S2P conversions, multiples, head waves, surface waves, everything. Okay. And for that, it uses an exact matrix propagation formalism. So the reason we want to use reflectivity that this is exact for 1D model, and this is analytic. Okay, in the sense that we have solutions that can be basically just derived by solving some equations, and this one though has to be, and the analytic solution is available in frequency wave number or frequency ray parameter domain, but then we have to, once we have the final set of equations, we can just calculate those in omega k domain, and then we can go back to offset time domain. So this will handle your PSP to S coupling and also free surface conversions. It naturally incorporates an elastic attenuation, because in the when you have an elasticity, what you do is you make your velocity, say Vp or Vs. Vp, you have a real part, and then you have an imaginary part. And this imaginary part actually is where we use the Q value. Since this is all done in frequency wave number domain, your velocities can be frequency dependent and complex. So remember this, when there is attenuation, your velocities are frequency dependent and complex. Okay. So we have this relation which is called Kennett's recursive relation, which I will be talking about in a bit of detail. That is unconditionally stable. So that is what made this method very, very attractive. And in earthquake seismology, this method is used for receiver function modeling, teleseismic waveforms, and of course, we have AVA analysis. And a lot of times, the finite difference calculations are compared against reflectivity methods, because reflectivity methods are, I would not call it fully analytic, semi-analytic, in the sense that in the frequency wave number domain, it's analytic, and then you have to do the computation for late media. Okay, so we assume horizontally stratified half space. So let's say that I have n layers, and here each layer is characterized by velocity, p wave velocity, shear wave velocity, and density. So oftentimes alpha, beta, and rho are used as symbol, but in many places you also see VP, VS, but they're the same thing. So each layer has alpha, beta, rho, thickness, Q alpha, and Q beta. Now, when there is anisotropy, then what you have to have is CIJs, right? As we saw last week or the week before, the CIJs are the coefficients of your stiffness matrix. And depending on whether you're using VTI or general anisotropy, the CIJ can have like 21 independent coefficients or 5 coefficients for VTI case. Now, this is interesting when there is an anisotropy. What is the Q value? Because as you saw in our Hooke's law, when we include attenuation, we had the viscosity term, and that also has 21 coefficients. So ideally, we have 21 stiffness coefficients and 21 Qs, and that is something we don't understand, in the sense that we don't have measurements, we don't know what they are. So for VTI case, there are 5 coefficients and you have 5 Qs, but typically we use P and Q because VTI has now 5 parameters: is alpha, beta, epsilon, delta, and what is the other term? Epsilon, delta, and
The density, sir? Or
no, PV, VSV, epsilon, delta, and then there is a shear term, right? Anyway, so there are 5 coefficients and then density, right? So here we can basically put in Q values for epsilon, gamma, sorry, epsilon delta gamma. Okay, but then again, this is approximation. But for now, let's look at isotropic layered medium. So what is the procedure? It's a bit involved, but not extremely difficult. So what we do here is we don't solve directly in frequency in offset time domain. We apply Fourier transform, and in 3D we can use Fourier transform both in. So we go from t to omega, and we go from xy to kx ky. Okay, and it turns out that if you apply these transformations to your wave equation, then you get an ordinary differential equation in depth only, because xy dependence, this is gone. And the reason we can do the transformation is that we assume that in the x and y direction the properties are not varying. Properties are varying only as a function of depth. So the next thing would be like, how do we solve this ODE? Okay, now there are two approaches. One is the propagator matrix approach, which became quite popular in the early days of analyzing seismic data. But then this reflection matrix approach, which is pioneered by Hooks and Muller and later by Brian Kennett, uh, actually became very popular. And I'll explain to you what is the difference between these two and why reflection matrix is more popular than the other methods. So, but this is all done in your omega p, omega px py domain. And then inverse transformation from p to x will give you offset, and from frequency to time will give you this. So finally, you get an XT seismograms. Okay. So there is a caveat here, is that if you assume if you in 3D, ideally you're supposed to take transformation over x and y to go to kx ky, but for many cases you can assume cylindrical symmetry, like the models are the same in different direction, and this symmetry is valid for isotropic media and for VTI medium. It's not valid for general anisotropic mediums. If general anisotropic media, you have to actually take transformation for kx and ky, but for isotropic and VTI medium, rather than using a Fourier transform, we use something called Hankel transform, and I'll explain very briefly what that is. Okay, it's not a lot different, but it turns out that rather than going from p to x and frequency to time, just you can also do something like just take the inverse Fourier transform. So go from frequency to time. So then what happens is you get the tau p seismograms. Okay. So first, if you did frequency to time, you get tau p, and then you can basically go from p to x. And this is what I was showing you earlier. So that is why I spent a little bit of time last week, or maybe the week before, on plane wave decomposition. And I'll just summarize what we discussed before. What we are going to do is to compute synthetic seismograms first in plane wave domain. So we will compute response to different plane waves, and then we'll basically apply a superposition of these seismograms. So when I say superposition, which is the same as what I showed you earlier, is a Fourier transform or Hankel transform. So first we have to define how we parameterize the plane waves. These are by ray parameters. We already talked about this. And ray parameter is sine theta over v. It's very easy to show that for isotropic case. And from kx, we can go to omega p, kz. is the vertical wave number, it's omega times q. So p is called horizontal slowness, q is called the vertical slowness. But when you have a 2D Fourier transform over x and y, then we have kx and we have ky. So this becomes px and this becomes py. But then px squared plus py squared plus uh, q squared or pz squared, square root of that is equal to what? 1 over velocity. Okay. Now, this is something that I talked about earlier. You can just do a slowness transformation, offset tau p, and you can go to frequency domain. But this is a linear transform. And like I said earlier, this does not give you correct amplitude. It will have a spreading term, which is square root of r, rather than 1 over r, what we have for point sources. So this assumes cylindrical source or the line source. Okay, but this will give you a decent kinematics in XT domain, and I'll tell you how we actually handle that exactly. So for each layer, we now compute the vertical slowness and horizontal vertical slowness for P waves and vertical slowness for shear waves. Okay, and this is very important that when it goes to critical, then this Q values become complex. So we have to choose the sign of imaginary part. And for P less than 1 over velocity, this is real and positive. When it's greater than 1 over velocity, then you have an imaginary part, Q plus IQ, right? Now remember, we have this e to the power I, let's call this Q bar, I, Q bar, and Z. So that's my phase term. And to make sure that it decays away from the vertical direction, we have to choose the right sign. And this is basically, you can use plus I or minus I depending on it's upgoing or downgoing. Okay. All right. So how do I choose how to sample my P domain, right? Like I said, we go from P to X. So slowness grid design, it's very important. Sometimes you see artifacts in reflectivity synthetics. And this could be because of not choosing the P grid adequately. So P min equal to 0 will give you the vertical slowness, vertical incidence. And you can choose the P max value to be 1 over the slowest velocity in the medium. Of course, in the elastic medium, your shear wave velocity is the slowest, so you take the minimum shear wave velocity. But in reflectivity calculation, you don't have to choose P max this. You can choose any other P max value. But that would mean you're restricting your calculation to that particular P max. And then delta P sampling is given by this equation, 1 over 2 x max f max. And also when you do the slowness integration, you can apply cosine or taper. Okay. All right. So now how to get to the correct point source in the transformation. It turns out I have not shown you the details of the algebra just for you to remember that rather than doing a Fourier transform or doing a tau p transform, you have to solve this, and this is called a Hankel transform, where the argument is a Bessel function. Now, the Bessel function of order n in general, but this is equal to 0 for PSB monopole and what 2 for dipole and so on, and r is the distance. Okay, so normally computing the you can compute the Bessel function as a series expansion, and then you can use that in the argument. And this is why people always have this wrong impression that the tau p transform forward and inverse does not give the correct amplitude because they don't do it right. And we have to do a Hankel transform. So at large distance, the Bessel function can be replaced using its asymptotic form, and that asymptotic form gives you this. And now here you see that there is a 1 over square root of r, and there is this phase shift. Remember in 2D, in the line source, I showed you that your pulse would look like this. If you include a delta function, it will look like this, and your spreading is 1 over square root of r. Okay? So these need to be corrected for, and that can only be done using the Bessel function in the integrand or asymptotic form of it. Okay. So then you can just straight away relate it to tau p. And in tau p, just wanted to remind you, if if you have these xt domain, they look like sum of ellipses for different layers. But here we're generating first tau p gathers and then going to xt. So this one can be transformed using if you want a quick and dirty result, you can do a slant stack, but otherwise you have to use the Bessel function or as its argument. It's asymptotic approximation. So if you have like all of these layers, now you can see that you have all of these individual ellipses and then the sum of this and then this. Okay. So one thing I commented that in P domain, we don't do ray tracing here. It's only because for each one of these, all I have to do is to compute my delta tau, right? Which is the vertical delay time. And this delta tau is nothing but 2 times delta z for a particular layer times the q, the vertical slowness, right? So we know the thickness for modeling purpose. When you do the modeling, we know the thickness and we know the velocity, and p is something that is an independent variable. That's an independent variable. So for a given p, I know what q is. Since I know the velocity for that layer, I can calculate delta t. This does not require any ray tracing, and you can do that for all angles. Similarly, when I go to the second layer, I simply compute delta t and just add that. Okay, so it takes the delta t from the first layer and you add it to the second layer, then gives you the second layer. So this is what goes on under the hood when you are actually doing the calculation. So now I want to basically show you a rigorous derivation of Kenneth's approach, which you at least for once you should see how it's done. So I'll start with the general equation for anisotropic medium. So this is our which equation is this? Anybody remembers? Speak up. Which equation is that?
Web equation.
Hmm?
Web equation. So this is Newton's second law
Yeah,
in
this is
mass
Newton's
into
second law,
acceleration.
and this
Yeah.
is your generalized Hooke's law. So this
Yeah.
is a wave equation. If you put the sigma term here, okay, then it becomes a this is a wave equation. But even you can call it a wave equation, assuming that you are using this in sigma. So yes, but this is Newton's second law. So now we know what is strain, and if we have the C as the stiffness matrix, then we can or tensor. In this case, it's a tensor. We haven't gone into matrix yet because I'm using dotted, double dots here. And for isotropic media, we have alpha and beta, which are essentially functions of lambda and mu, and lambda and mu are the two stiffness coefficients. So as I showed you earlier, when you are in an elastic medium, you have, let's say you have this ray, this is our plane wave given by this ray. So P wave for isotropic media is polarized along the direction of the ray. And as V is normal to the ray on the same plane, and SH would be perpendicular, right? SH would be in a plane that is perpendicular to this. So it turns out that for isotropic reflectivity method, PSV can be computed independently of SH. And this is also true for VTI case. But for full anisotropic medium, there is no decoupling, and also PSV and SH definition does not quite hold there. So we have something called P, S1, and S2 because these are quasi S waves. Sometimes they can be at some angles, they can, or some ray parameters, they can be pure SV or pure SH, but they are not. And also this QP, this is generally sent as QP. Now these QP waves are also not always not always polarized along the direction of the ray. But reflectivity method can handle all that. Although I'm not gonna do fully anisotropic demonstration here, but we have codes for doing that. Okay, so first we define a trace displacement vector, which is basically the two components of displacement and two components of stress. And here what you see is that these are basically the vertical component of displacement. This is vertical component of horizontal component of displacement. And I'll show you that we can now derive a system of ODE. So this is going to be our new wave equation under the assumption that the medium is layered. And this will have this B, and this A is a systems matrix, and it's a 4 by 4 for PSV case and 2 by 2 for the SH case. So this basically requires that we solve B as a function of Z, omega, and P, right? And this B is basically contains all the physical variables that we want to compute. All right, so bit of algebra, and I'm not going to go through every step. So let's do this. Let's do this ODE for general general anisotropic case transformation. Although it's not necessary to do this for isotropic case. So here I'm showing you our Fourier transform going from x to pxpy and t. Okay, and this is our inverse Fourier transform. So we will derive this equation that I showed you in the earlier page. Okay, so let's see how this is done. Again, these ones are also small, and deliberately I've done that so you can fit everything in one page and not all the details are necessary. So if I write it in individual components or in initial notations, then we can write our Newton's second law of motion for kth component of displacement here. And this is my stress. And there is a derivative with respect to del xi. So this basically means del I here means del xi. And there is a sum over repeated indices. So the k is what is basically left over. And then your constitutive relation is given by this. So what we do here is now we expand these notations, and what we get is a system that looks like this. And then here we will use our we'll specialize to isotropic case, and we put down, we'll also use void notation. So C1111 is C11, and that's our lambda plus twice mu, which I talked about earlier, I think in the first lecture. And this is lambda, this is mu. Once you plug it in, then what you see is we have these 7 equations. Okay. So here, for each one of these, we rearrange those terms, and then we get this matrix formulation. Okay. So what we have on the left hand side are, this is our components of displacement. Remember, our displacement vector u has three components: u1, u2, u3. And our stress, I can now write it as a column vector tau, and this has six components because you can say the tau 1 1, tau 2 2, tau 2 3, tau 1 3, tau 2 3, and yeah, there are five components. Okay, so now there should be six components. Okay. So we have also used the symmetry here. Okay, so we have u1, u2, u3, tau 1 3, tau 3 3, and tau 2 3. Okay, so then what we do here, that comes out of those equations. So now what we have is a system of ODE. I can write this as a vector A. I can write this as a matrix UA. And what we have here is this. And this, again, this can be written as B. But we use a different term for B. I'll show you in a second. So now we can set Py equal to 0 for the isotropic case. And that gives us a PSB and SH. Now this is the reason I showed this is because this is what you need to do for the anisotropic case. For isotropic case, you don't have to do this. You can start with Hankel transform rather than Fourier transform, and you'll have a system for the PSV case. Okay, so now how do we solve this? Okay, so first we'll look at something called propagators and Will propagators. Okay, so what is propagator and what is Will propagator of our system? Okay, so here it's a bit mathematical. I don't know how many of you remember your linear algebra. So if you have a matrix A, you can write this as D times lambda times Z inverse. Okay, and this D, each column of D is an eigenvector, and lambda is a diagonal matrix. This lambda is a diagonal matrix. It has lambda 1 1, lambda 1 2, and so on. Okay, so if you did that and you plug it into this, and now we define, so this D, so now we can say that we define a vector V, which is D inverse B. And if you did that, then you get an equation that looks like this. Okay, and it turns out that you have something called I omega. This is I omega lambda here. Now this, when you first look at it, you might start to wonder, like, why do we need this, right? But what you see here is that if you want to compute V, which we'll be calling a wave vector, you can simply take the response at V Z naught, at depth level Z naught, and you're going to Z simply by multiplying with this term. And this one is basically essentially looking like a phase shift, right? Except that I haven't told you what lambda or the eigenvector, eigenvalue matrix looks like. So then we can define this as a wave propagator, this whole thing. I said this is my Q. So then we can say that I can go from VZ naught to VZ using this wave propagator Q. Okay. And then we will define this something called a propagator matrix. And this propagator matrix, you will see, is this. This propagator matrix Z naught to Z has this eigenvector matrix, inverse of that. And this is eigenvector matrix, and this is your e to the power I omega C. So the reason this is quite interesting is that when your z equals z naught, your this is d times d inverse. So then P becomes identity matrix. Okay. So this one checks out. It turns out that when you have a large number of layers, all that we have to do in this particular method is to go from z naught to some depth z. You simply go z naught to z1, z1 to z2, zn minus 1 to zn, zn minus z. So this is actually looks like a pretty simple thing. It's a cascaded multiplication of propagator matrices. And it turns out that this V can be computed from this. And this eigenvalue matrix that I showed you, this is nothing, this will have the vertical slownesses here. So that is applying the phase shift. Okay. So if you have this, so now we look at the wave propagators. This is given by this particular equation. And here, if you have a discontinuity, then you have to propagate up to here, then through this, and then through here. Now, it turns out that uh, if you just look at this Haskell, so this is once the propagator matrix was derived, people actually used this to compute synthetic seismograms. And this became quite popular for a long time, simply cascaded multiplication of this. So the problem with this method is that for large frequency depth products, the propagator contains some error, that it grows as you multiply with multiply for different layers, and this exponential becomes so large that it actually blows. So multiplying for many such matrices can cause instability, and it does cause instability, and that is why Kenneth's method actually became so popular. Okay. Now there is a way you can actually modify this using something called um, there's some other method that you can use. But then Duncan, so there's a method proposed by Duncan where he said that I can change this to from 4 by 4 to 5 by 5, and that gets around the instability problem. But then the propagator matrices for anisotropic medium becomes very, very complicated. So that's one of the reason why Kenneth's method is useful. First of all, it is unconditionally stable, and it can basically extend to anisotropy without much effort. So if you have a reflection matrix approach, this is unconditionally stable. Is you can derive the. I still haven't finished talking about reflectivity method. We're somewhere in the middle. But I just wanted to show you the advantages. Unconditionally stable, you can compute the derivatives for MWI, and they can be computed by semi-analytic method. You need to do a little bit of careful coding, but I would probably take that take that bullet out, because nowadays, you can with the invention of Python and all those, so matrices can be designed very, very quickly. So this is probably no longer valid, and it's most efficient for an anisotropic medium. On the other hand, this compound matrix approach of Duncan, it is also unconditionally stable. It's actually even faster than Kenneth's approach, but for general anisotropy, it's very, very slow. Okay. And the other thing is that in Kenneth's approach, you can pick and choose what order of multiples you want to keep, and whether you want to include shear wave, whether you want to include surface waves. But that stuff you cannot do with compound matrix approach. All right. So how do we then do transmission and reflections? So this is actually uh, I've given you some derivations here, and I would highlight the main thing that is derived here. So here we have this particular scenario. We'll look at wave from above and wave from below. Okay, plane waves. Don't forget. So we're talking about plane waves, and if you did that, you can actually come up with an expression for something called reflection and transmission matrices. So now here we will show you there are four matrices: RD, PD, RU, and TU. So this corresponds to reflection matrix, reflection coefficient matrix for downgoing wave. This is transmission for the downgoing wave. This is upward reflection coefficient. This is down. This is upward transmission coefficient for the two scenarios that I talked about here. Okay. So now this RD can have this kind of structure. This will have RPP. It will have RPS. Then you have RSP and RSS. Okay. And this is going to be 2 by 2 for the isotopic case. And I'm showing you as 3 by 3 because this is for general anisotropic case. So there can be conversion from P to S, both in the uh, X direction and Y direction. So we can have a PP, you can have P1, P2 shear 1, P2 shear 2, and so on. But for isotopic case, we don't have to worry. So we have RD, TD, RU, TU. So these are 2 by 2 matrices for each layer that holds reflection coefficients. And these reflection coefficients, you can show analytically that they are nothing but Zoetis coefficients. Okay. And then, so this is what I was showing you: TD, RD, TD, TU, RU, TU. And it turns out that with all of these, we can now come up with an expression which looks like this. So you can have RDTD, RUTU. That is what you are propagating through the stack. And these are omega p domain. Each one of these is omega p domain. And you are computing those through each layer. Okay. And then you're using something called iteration equation. So what this is telling you is that if I have response from, say, I have, this is my zone layer 1 or zone 1, and this is my zone 2. If I know the response of zone 1 and I know the response of zone 2, I can get the response, complete response of 1 and 2 by using this equation, which is my Kennett's iteration equation. So here what we have is this equation, and then we can expand it here and examine each term. So the first term is RD1, 2. So I'm reading from right to left, okay? So this one is 1, 2, the reflection from this layer. Then have transmission 1 to 2, then reflection 2 to 3, and transmission 2 to 1. Then you have the other terms. For example, this is one where you have TD1, 2, RD3, 2. Then you have another transmission. Then you have RU1, 2, another transmission. Then I have RD3, 2, and then TU1, 2. So what you see is that this compact term includes everything, all the reverberations, which is what we want. But if you want to compare or you want to test out, like, what is the effect of certain order of multiples, you can explicitly code it using, 2 or 3 terms or 4 terms, and you can actually see what the response looks like. Okay, so that is one advantage of using this method. And we have similar term for TD and RD, RUTU, and other terms, and they mean exactly the same thing. So this
So
is this
those
is yeah.
so those higher terms are higher order reverberations, which we are truncating. when you're expanding RD
Yeah,
on
yeah, I
Q?
didn't write all the terms, yes. But if you
Okay,
look at all of these terms, you'll see that it basically has all of these different terms here. Okay.
okay, yeah,
Yeah.
thank you.
So it includes everything and doesn't matter whether the layer is thin or thick or anything like that. So all that you need to do is to compute reflection coefficients, Zupritz, right? And the phase term. And the phase term is nothing but e to the power I omega qz. And whether it's an upgoing or downgoing wave, we have a plus sign or minus sign. Okay. And the whole response is built in using these reflection and transmission coefficients. They are parts of RDTD, RUTU. Okay. So if somebody wants to ignore all that theory of Kennett approach, all that the person needs to remember is that I need RDTD, RUTU and this equation. Okay. And then the transformation. So this is the general flow chart. So you loop over array parameters, loop over a number of layers, compute reflection and transmission coefficient for all the interfaces, then loop over frequency, and then each time you compute RDTD, RUTU, you use iteration equation to update that, right? It doesn't matter whether you are going from top layer to bottom or you're coming from bottom to top. It will not make any difference. However, this particular loop that I have here, I have the frequency loop as the innermost loop. Okay, and that means that I'm assuming that my velocities are independent of frequency, right? Because I'm computing the reflection coefficient before I'm putting it in the frequency loop. But if you want to include Q here, which is frequency dependent, you simply have to swap these two loops. Okay. So once you have computed these two loops, so here I have P response, right? P omega response for a single P. And then I can simply do a inverse Fourier transform to go to tau, still in P, okay? And once everything is done, then you can go to xt domain after integrating over all array parameters. Okay?
Sir, where does Joffrey's equation fit into, sir? Is it the
Yeah,
reflection coefficient,
yes,
individual
yes,
reflection coefficients?
yes. For all interfaces.
Okay.
Okay? Yeah, yeah. This is so it uses Zoplis coefficient. And for anisotropic medium, of course, you don't have analytic form, so that has to be computed by solving an eigenvalue problem. But you can, for now, you can ignore that. For VTI, it's analytic. So this is the most important sort of like diagram, and it took me like almost an hour to get to this, but this is the heart of the algorithm. If anybody wants to know what is going on, it's very important for you to know what is going on. So it's very important to choose your delta P and omega and T, all of these things carefully. So you can pick those parameter. So let's say that I want to go to a certain T max value, right? This is the maximum time that I want to look at into the seismogram. So then your delta omega is going to be 1 over 2 pi T max, right? And similarly, you can you can choose a delta P as I showed you in the earlier equation. So here, what kind of argument is going to be in the integral? Here you have to have the Bessel function. Okay. Otherwise, your amplitudes and phases are not going to look quite right in the seismogram. So this is how we have calculated this. So this is 2 layer over a half space, primary P only. So this has been computed. I've computed this using reflectivity. And I've chosen to keep only the primaries here. Okay. And this is my, for the elastic medium, this is the P, this is the vertical component, and this is the horizontal component. This is like two interfaces. I think I showed this earlier, but I didn't say how I computed this. And if you go from tau P to xt, this is what it looks like. And then here I'm just putting in internal reflections, internal multiples, all P and S waves. You can choose also to only put in P or only to put in S multiple just to see what the response looks like. And then you can compute the synthetics. That is what it looks like. But then once you put in, this is internal multiples, and then we can put in the full thing. Okay, so here we have this is your full waveform, and this is your convolutional model. You can see the differences or blocky models. And finally, I want to show you one VTI model. So here there's a log, and this is basically your alpha naught, beta naught, rho, epsilon, and delta. And then I show you my synthetic seismograms in XT domain directly. So this is your isotropic case, and this is VTI case, and this is the difference. So what is the difference here? Anybody? See, the differences are going to show up at large offsets, right? Because of the effect of epsilon and delta, because these velocities are not now now angle dependent, right? So the travel time is not going to match at high angle or large offset, and also the amplitude is going to be different as you go to higher offsets. Okay, so the effect of anisotropy, you can see depending on how strong the anisotropy is, you can start to see those right from the intermediate offset range to large offset range. Okay.
Sir, one question, sir.
Yeah.
In the last step of your flow chart, when
Yeah.
you said integrating over the plane waves through the Bessel's function and getting the point source response,
Yeah. Yeah.
here the spherical divergence will still need to be addressed in the when
No,
you're
it
doing
is.
the inversion kind of thing.
No, this synthetic, this is a forward problem, right? So this already has the spherical divergence because of the choice of this.
Okay.
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 But
Okay.
if you go to P domain, then there is no spherical divergence. Okay. So
Hmm.
for inversion, your data is in XT domain, right? And
Yes,
you
sir.
want to go to tau P domain, and there you have to use a Bessel function in the argument to go to tau P domain. Okay.
Okay.
Okay. Yeah.
Okay.
So yeah, I wrote a tau P transform code, I think um, several years ago, and that has all of these options, and you can see the differences. I don't. If you like, I can show you some result next week. I didn't come prepared with
Okay.
that.
Okay, sir. Yeah.
Yeah. Yeah, I can show you the effect of different choice of like a linear transform, Bessel function, Hankel function, asymptotic approximation. Okay.
Okay, sir.
Okay. So yeah. So this is basically your algorithm. And another thing is that this is not very expensive, but each ray parameter calculation is independent of each other. So you can do this in a parallel mode. You can have different CPUs running different calculations. You don't need that for isotropic case, but for anisotropic case you do to make it faster. So this is what VTI looks like. And finally, we have this reflection coefficient matrix, compound matrix. I just wanted to remind you this. So that concludes this talk. And before I do that, I can say that the ray-based approach that I showed you earlier to describe 1D modeling, this can be extended to heterogeneous 3D media, and which I'll talk about next before we talk about bond series. But we need to be able to keep track of reflection and transmission and apply Snell's law locally. And this is something that is done automatically in Kenneth. All you have to do is to look at the first and second reflection. And then we can compute. So in the general case, you can use different equation for computing the ray paths and then different equation for computing amplitude. And I'll show you then after a little break. Okay. So that concludes my first lecture. And before we take a short break, let's see if you have any question. Is there any part that you want me to go over? Okay, if not, then let's meet at in about 10 minutes. Can you see my PowerPoint?
Yes, sir.
Okay. Okay, so now we'll move to laterally heterogeneous medium. So for this morning or evening time of yours, we discussed layered medium, where the properties are varying only in depth. Now we will go to make the medium more complex. What that means is that we're not going to be able to get any analytic solution like what we got for the Kenneth's method, which is exact for in omega p domain, and then the rest is basically numerical calculations of these. So here, like I said, when the medium is very complicated, we don't have exact analytic solution. Okay. So what kind of choices we have? One is to get some kind of approximate solution, or we can do numerical. So we can get numerical solution, right? So here we'll first look at approximate solution that is valid at very high frequency. Okay. So once we have made this approximation, I'm going to show you that we can have closed form solution for amplitude and things like that. So how do we do that? Again, we will start with the wave equation. And here I will, just for demonstration purposes, I will stick to acoustic wave equation, even though the same kind of analysis can be done for elastic media, but that makes your algebra a bit messy. So I will just stick to acoustic medium. So this is our constant density acoustic wave equation, where the P is a scalar field. It could be pressure, depending on what kind of equation you are using. And we will transform this wave equation to frequency domain, okay? And that gives us our famous Helmholtz equation. So what we have here now is omega squared by c squared. You have seen this repeatedly during my presentation. So this omega squared by c squared is our wave number k. And on the right hand side, I have the source term. So the question is, how do we actually solve this equation when velocity, which is given by c here, is a function of x, which is x is basically your, it could be x1, x2, x3, or xyz. Okay. And we know that the Green's function is defined by the solution of the equation when we have a delta function in the right hand side. As I explained to you, I showed you how to derive Green's function for a homogeneous medium, and today we'll show you how to derive Green's functions for inhomogeneous medium using some approximation, because you can't get analytic closed form solution for the Green's function for general heterogeneous medium. Okay, so then once we get the Green's function solution, then this is basically a convolution of the Green's function with the source, and that gives you the response gives you the pressure response that you are interested in. And we know that for homogeneous medium, this is the Green's function. I derived this in my, I think it was in the first day or second day, I don't remember. And if you remember this is essentially the phase term. And this is for plane waves because K naught basically gives you the wave number. And that's your spreading term. Okay, so for spatial, like I said before, for spatially varying Cx, we don't have a closed form solution like what I showed you in 5. So here we'll make use of high frequency approximation. So how high is high frequency? But that's something that is not rigorously defined. You'll see that for all of these, essentially ray theory is said to be valid for infinite frequency. But then it works quite well even at very high, I mean, even at reasonably low frequencies, except for the places where it breaks down. Okay, so what we will do here is we will try an ansatz. Ansatz means trial solution. I don't know if you're familiar with this term. Mathematicians use it a lot. And we will try to get a ray series solution. Okay. So the physical motivation for getting trying to get a high frequency solution is that when the wavelength is short compared to the length scale over which the velocity is varying, then the medium appears to be locally homogeneous. Okay. So there is a difference here in terms of how we are trying to handle this. For the Kenneth's method, we say that medium is homogeneous, layers separated by some discontinuities. In this case, what we are saying is that a medium is such that the wavelength is short compared to the length scale, so it could be locally can be treated as a homogeneous medium. But then what we really have to see is how we can compute the travel time and the amplitude. So as we saw in the previous solutions that we have an amplitude term and a phase term, right? The phase term goes to that basically is dictated by the travel time, and amplitude is a function of material properties. And of course, the phase term is also affected by the material property like velocity. So what we do is we try a trial solution. Say that, okay, maybe we can try this solution. So do a back calculation that this is a phase term, and we're not going to define this yet as to what form it takes. And there is an amplitude term. And then we say that we can write this as a series in frequencies, so the sum over different frequencies. Okay. So then what do we get here? If you plug this in here, and then if you plug the solution in your wave equation, take that solution and plug it in here, not in this one, plug it in here in equation 3. And now you start to collect some terms, okay, of different order of n. And what you see is that this is your grad u and this is your del square u. And adding this, we have a term that looks like this. So these are of the order of omega squared. Now, collecting all powers of omega, so this is going to the power of omega squared, omega 1, and omega 0. If we ignore high order term, then what we have is this equation. Okay? And from here, now we have this famous equation, It's called the Eikenel equation for the phase term or the travel time term. So here, what we have done is we have thrown away terms of high order and frequency because they were appearing as 1 over omega square. So you're saying that omega is so large that 1 over omega square is small, and we can throw those terms away. And that high frequency approximation, we get an equation that looks like this. Shows that the gradient of travel time squared is equal to 1 over c square, that is your slowness square. Okay? And this is the Eikenel equation. So it's a first order nonlinear PDE. It's also called a Hamilton-Jacobi equation for the travel time tau. Now, all of these things you can find in optics, quantum mechanics. They've used all of these, all this math. So, for the physicists, for the physicists to have, for the physicists, these are not new, but for geophysicists with strong background of physics, they shouldn't be all that difficult to conceptualize. So now the surfaces where tau is equal to a constant, these are wavefronts. And this vector is everywhere normal to the wavefront, and this is the slowness vector. And the direction of the unit vector is tangent to the ray. Okay, and we'll explain that in a second. So if you solve this equation, you'll get how the travel time is changing as a function of frequency, as a function of x. And from the gradient of the travel time, you can also look at the ray paths. Okay. So one of the ways people solve this, and you can find this in classical mechanics as well, is that you can come up with some characteristic equations where the sigma is the length. So this sigma is the length of the ray path or arc along the ray. And oftentimes people also use something called ray-centered coordinate system where the distances are measured along the ray path. And the travel time is now basically Sxx delta P. What this means is that if you want to compute the travel time from this point to this point, you have to integrate this. So within each interval, you take the reciprocal of the velocity and multiply by this length. So this is very simple. Okay, so it tells you that you can break this path as homogeneous, and within each small path, you simply use the straight ray approximation for this. Okay. So, and then we also have Hamiltonian formulation. These are equivalent, and from there you can get this Snell's law as a consequence, which I'm not going to go into details of. Now, there's another important equation that comes out from this derivation is that if we look at the leading order amplitudes, this gives you an equation for amplitude that looks like this. And why have I used 0? Because if you look at my ray series here, I have n equals 0 to infinity, so I'm only keeping terms that n equals 0. So these are the 0th order approximation. So this one gives you an equation that looks like this. And if you just expand it and do all of that algebra, you get this equation, which is your transport equation. Okay. So we have two equations. One is your Eikenel equation. Another is your transport equation. So Eikenel equation gives you travel time, and transport equation gives you amplitude of the ray path. All right, but what is our goal? Our goal is to now see if we can compute, if we can come up with a closed form solution for Green's function under this assumption. And so then what we can show that now I can get my ray theoretical green function, which is the leading order, has an amplitude term that is controlled by L, which is basically a geometric spreading term, and this tau is the travel time. Now, if it's a homogeneous medium, you can show that this is nothing but R in 3D and square root of R in 2D. That is the distance. Okay, so the spherical spreading or cylindrical spreading, depending on whether it's 1D or 2D. But otherwise, this needs to be computed using this equation, and that involves something called a Jacobian. Okay, and this Jacobian has been derived by a couple of different approaches, but at the end of the day, what you have here is this Jacobian is essentially, if you have a ray coming up to here, then you actually consider a small ray tube, and this Jacobian gives you the area of the ray tube. Okay, so what happens is that when the rays are coming together, then your amplitude increases. However, when there is a crossing of rays, your ray tube thickness becomes very, very small, so your amplitude blows. And those regions are called caustics. So ray theory is valid in regions outside of the caustics, and it is not going to be able to compute Green's function in regions that are in shadow. So shadow zones and caustics are the places where ray theory fails. Okay, so let's see how we can actually use this Eikenal equation for say ray tracing or for travel time calculation. So this is your Eikenal equation, and for a ray, for a source, you want to know the receiver. So given you want to know the ray path connecting source to the receiver. For the homogeneous case, you know that this is a straight line path, right? So if I, without looking into the equation, if I were to ask you, what is the path that connects the source to the receiver? What would be your answer? Because so many paths are possible connecting source to the receiver, right? So, this comes from Fermat's principle that the path for which the travel time is stationary or minimum, right? That gives you your solution to the ray. So if you look at linear velocity gradient, something like this, then you can show that that your rays are circular arcs in the medium. Okay, and as a function of x and z, I mean you can compute x and z using this. So the ray path in a positive gradient, you can see that it turns when this vertical slowness becomes when the ray becomes horizontal. Okay, and so because your vertical slowness is changing as you go deeper and deeper. Okay, and then they come back. And if there's a negative gradient, then it just goes all the way down. Now you have to worry about this because when you're talking about the full waves, you have to include these paths, and you have those turning rays. Okay, and then for the linear gradient, you can calculate. You have analytic expressions for the travel time. But for general anisotropic medium, general medium, general laterally varying medium, we have to compute this numerically. So there are methods. The shooting method, bending method, and finite difference or brute force approach. And I'm going to show you these methods. So here is a set of ray diagrams through the ocean layer that had some velocity gradient. You can see how the rays are turning. And if you then it gets reflected, and then if you have a barrier, it gets truncated here. But you see there are these diffracted rays that are not included in the ray method. So shooting method, one approach would be to discretize your velocity model, and we have this ray coordinate x, k, y, k, and z, k along the ray path, and vk is the velocity at x, y, and z, and this is the takeoff angle and how it's changing as a function of this. So in 3D, you have both phi and theta. It's shown in here in this diagram. And then these are your update equations. So these are your gradient in velocity in x, y, and z directions. This is your x update. This is your y update. This is your theta update, and this is your phi update. So given all of these updates, you can choose what delta z you want to increment over, and then you can calculate these. Okay, and then you go to the next step and so on. So this is one way you can compute the ray paths. So that is what I showed you. But then in here, this is the method that I've used. So here you can see that you have control over shooting the ray, but oftentimes we are interested in computing travel time for a given source and a receiver, right? So one way of doing this would be to trace a whole bunch of rays and see the rays that bracket this, and then interpolate in between to get the travel time. But there is no exact point-to-point ray tracing possible in this method. So this interpolation becomes a serious problem also. When you have like multiple ray paths, if you have rays that are going like this and then they turn and they come here and all of those things, it becomes very, very complicated. So again, the assumption is that the velocities vary smoothly in this particular method, and the discontinuities, you have to treat them especially by putting an if statement and deciding if the velocity perturbation is very high, then you use local Stain's law. Now we look at finite difference Eikenel solver. It became very popular because for migration, what we need is, let's say that I have a velocity model. And typically I define my image domain in say XY, XZ or XYZ in 3D. And within each block, I define velocities, right? So I have the source, I have the receiver, the trace is here, and this is my medium. I want to know what is the travel time from source to the receiver, but we also like to know the travel time from source to every grid location, because that's how I do my Kirchhoff migration. So it's not possible to do that using ray method because, well, without making serious errors, because there is no way you can guarantee that what you're shooting from here will actually reach here. So that's when this finite difference kind of solvers became quite popular. So what they do is essentially solving this. So they compute this gradient by finite differencing. So this is your one-sided difference. This is positive side, this is negative side. And then you look at these gradients and you put it in the Eikenhower equation and then solve it for the time. So the way it works is this. So let's say that you know the travel time between these points and you want to compute the travel time here. Okay. So you calculate those gradients and then decide which one is the minimum here. Okay. And then you proceed further. So this one gives you the first arrival only. Okay. The minimum path. And this is used in many of the migration algorithms, Kirchhoff, beams, and all of that stuff. And then he can solve this local quadratic, and that gives you what the travel time would be. Then there is another method, it's called ray bending method. So the first arrival methods, like I showed you, the finite difference based method, I'll touch upon that method a little bit later also, is ray bending. The reason we want to look into ray bending is that it basically is motivated by the fact that these methods do not give you the ray path explicitly. You have to compute from those gradients, and they return only the first arrivals, missing later branches. And the reason this is not all that useful, this may not be all that useful, is let's say that I have a strong velocity discontinuity here. And I know that this actually will develop head waves up to some time, right? Now these head waves are the first arrival here. Now this is my reflection and this is my head wave. This head waves actually travel faster than your primary reflection. But then these are not the most energetic arrivals. So when you do the migration, just focusing on first arrival actually does not help you to image the reflectors. So this method, ray bending, is actually quite slick because what it does is it uses the basic equation like this, Fermat's integral, where this velocity is, the travel time is Sx dl equals to 0, and the perturbation in travel time would be perturbation in this equation. And what is done here, before I go into a little bit detail, is that let's say that I have this point, I have another point, and I want to know the path here. So what it will do is it will give it a starting solution, say straight ray path. And now it will use Eikenhower equation based methods to bend the ray, either this way or that way, and see which one is the one that satisfies my Fermat's integral or the minimum travel time path. Now, to calculate the directions in which it's supposed to bend is what makes use of Eikenhower equation based formulas. So here, we still assume smooth velocity models, and we assume an initial path, and we perturb the initial path using a geometrical interpretation of ray equations. Okay, and this is our basic algorithm for ray tracing in general. So the way they compute this bending functional is that let's say that this is your tau, and it for each ray path basically is integration over this. Then you can calculate the gradient and then use that to do this. Okay, so here is a diagram. So this is your, let's say, initial ray path, and this is your true ray path. So once you have, so now you look at different points along the ray, and then you want to move them along certain directions. So this is the direction of the normal, in the direction you want to go. And this is what that formula has given you. And once you do that, then after a few iterations, you will get a ray path that basically matches your solid line. Okay. And the details, so then we have to minimize the travel time formula, which is an optimization problem. And here you can use conjugate gradients. So here, let's say that this is my dashed line, and this is the distance to which you want to bend the ray, and this gives you the distance. This one gives you the direction in which you want to bend the ray. And this you do for selected number of points along the ray path, and then at the end you will get a. And this actually works beautifully, and I even wrote a code many years ago for calculating travel times. So this is the this is one way of doing this. So typically, what you do here is that we have two loops, at least in our algorithm, where we first pick a course number and a course set of points, and then we define it as a function of iteration to get to the optimal ray path. And here by this method, you can also show the ray, and also you can show the travel time. And this is called a 2-point ray tracing because here you're actually bending the ray. And this is an approximate method for doing that. There are some methods that talk about 2-point ray tracing, but I'm not going to go into details of that. This is actually one of the best methods. So this is the schematic diagram for computing in a grid. So what we did here is first we start with the straight ray path, and then we bend it, and that gives you this. So what we do for when you go to the next grid point, we take this as my initial guess and bend it, and it will find this one. And this actually works beautifully. One of my uh, earliest PhD students, Farooq Akbar, he developed this, and this is actually quite useful. So there is an outer loop that is activated along the left edge of the model. Having found a ray along the edge, the reflection calculation of for the next grid is initiated. And then we are once we have the grid locations, you can calculate the travel time and sum those. And this is actually not very slow. It's actually quite good because in a grid you can always find a very good starting model, rather very good starting ray. So for this finite difference based direct method, which I talked about earlier, the way it goes is that you search in different directions, different columns and rows, then pick the minimum time. And this is some detail that I'm going to skip. And we extended this to anisotropic media for both VTI and TTI. One of my students, Dhananjay, actually did his PhD, and we were looking at some data, marine data that had TTI kind of anisotropy. In those days, 15 years ago, we couldn't do full finite difference solution of wave equations, so we're looking at approximate methods. And we came up with this. So we calculate the group velocities, and then from there we have these coefficients in the group velocity. And then first we try to see how it compares. So this is group angle for group velocity, and this is for TI and TTI media. And our approximate method actually does a pretty good job. But for some stronger anisotropy when delta is negative, then we had some issues. But overall, it was actually not too bad. So we used that approximation. Otherwise, getting to group velocity is not that simple. So here, compare three different travel time algorithms. First of all, for isotropic case, this is a very old paper, but still I like it. And you can see that, oops. Here we have first arrival, and this is from our bending method, and this is from the shooting method after interpolation. So this one you can see very clearly is actually capturing head waves, which is not desirable, and that path is completely avoided by these methods. So the Eikenal equation and ray-based travel time methods. In the Eikenal equation, this is the Eikenal equation that governs the travel time. The transport equation provides the corresponding amplitude. Shooting method is explicit ray paths, but no guarantee receiver hit. Pseudo bending iteratively minimizes Fermat's integral, handles refracted waves, and requires smooth velocity model. And this finite difference based method, which I talked about, also propagates travel time onward at a grid. And TTI, VTI can be incorporated via Fourier expanding the group velocity expressions, like what I showed you earlier. Okay, so that concludes this particular chapter. Questions, comments?
So these equations are broadly an integration based methods, unlike the partial differential. Is it? Am I
Well, you
understanding
see,
correctly?
you are starting with partial differential equation, and then solution is in terms of integration.
Right. So integration is supposed to be simpler than the derivatives, especially partial derivatives. Is it something we can
No, not
assume? Or?
no. This is just manifestation of the way the solutions come out, because the ray paths are, basically you have to integrate along the ray paths to be able to compute the travel time. Yeah.
Okay.
Anybody else has any comment or question? Not much interaction from the audience.
So
Okay.
these equations are mostly for the travel time, or we can create synthetic seismogram as well, because we have the transport equation as well.
Yeah. You can compute the synthetic seismogram, ray theoretical. So you have the amplitude and you have the travel time. So that gives you Green's function, right? And then you
Yeah.
can convolve it with a wavelet, and that gives you yeah, you can generate synthetic seismograms also, ray theoretical synthetic seismograms for sure. Yeah.
So is this similar to the method by Helios? Uh, they also use Green's function and integration to calculate synthetic seismogram.
Yeah, I will talk about that next.
Okay. Okay.
Yeah. I don't know about the Helios method, but they're using Born approximation, right? I've seen that paper. So yeah, so
Yeah.
that is my next topic. So
Okay.
just give me like 2 minutes and then we can start. Okay.
Sure. Sir. Sure.
Okay. So now our focus is on today our focus has been after Brian Kennett's reflective method, focus has been on asymptotic method. So here I'm going to talk about two methods, the Kirchhoff and Born series. And you must have heard about Kirchhoff method for migration and the Born migration, Kirchhoff migration sort of used synonymously with when we talk about true amplitude, we talk about Born. But what I wanted to just mention one other thing in the passing is that we have this reflectivity method for forward modeling. Then we have this Kirchhoff method for forward modeling. Then we have finite difference method for modeling. And there is a parallelism with migration methods also. So you have FK migration, we have Kirchhoff migration, then we have reverse time migration. So these are essentially based on the same theory, just that used slightly differently for migration purposes. So it's important that you understand these theories. Okay. So here again we'll start for Kirchhoff integral. I will start with this Newton's second law in the frequency domain. This tau is the is the is the stress second order stress tensor. So this V, now consider a volume V. and there is an outward normal n, and this del v that represents the surface. So now we can think of a distribution of body force which is outside of V. Okay, that first one I showed you is inside the volume. This is outside of the volume. And this has the stresses and displacement. This stress and displacements as U2 and tau2. On the other hand, this one is, okay, so now we have this is from outside, and then inside we have U1 and tau1. Okay, so then we use, sorry, this thing didn't come out very good. So these are all dots, okay, dot products. So now we can look at take the difference between these two equations, and then we do the integration. Then what we can find is that this is valid for elastic anisotropic medium, but it's much simpler for the acoustic case. So what it tells you is that if you want to basically compute the response U1 at some point x2, which is here, the F1 and F2, these are the sources. One is outside, one is inside the volume. Then this is given by simply by knowing the displacement and stress field along the surface. Okay. So what it means is that if you want to compute the response from source to the receiver, if you know the field from source onto this and field from receiver onto this, integration along this line will give you this. Okay. So if you have an interface and then you break it up into small number of points, and then you can say that this is my source, this is my receiver. So you have all of these ray paths, and if you sum along that, it will give you the stationary path, which is the Snell ray path. Okay, and that is the idea about Kirchhoff method for forward modeling. And the reason we like it is because this surface does not have to be flat. And the other thing is that if you have a truncated reflector, you will also see diffractions from here. This method gives you that, which is not handled by ray theory. Okay. So the only thing is that we have to know the wave field here from the source and from the receiver. What it means is that you have to know the Green's function from source to the scattering point and from receiver to the scattering point. Okay. Now, so I already showed you that. So you can use the Green's function from the ray theory. So here, if you have, so let's say that this is my reflector, and I want to compute the reflection from this reflector. So then I can calculate my wave field from the source onto this and from the receiver onto this. And then once I have all of these wave fields computed at this points, I can integrate along this, and that gives me the reflection. That sounds like a magic, right? But if you think about this first intuitively, if you have one point here, then that basically gives you diffraction, right? So if you have a whole bunch of rays here, whole bunch of scatterers here, part of the diffracted waves will destructively interfere, and part of it will be constructively interfere. And then when you are at this reflection point, it is this path that will be the most dominant path. And that is called the stationary path. Okay. And you can actually show this analytically. Also, I'll show you in a minute. But then if your reflector is undulating, it's not flat, then let's say that I have a reflector that looks like this. And if I have a source and a receiver right there, then we have multiple ray paths possible, right? And this Kirchhoff integral will give you all three paths because all of these are stationary paths. So when I say the travel time is minimum, it's not correct. It should be stationary. Okay. So how so what is the stationary path and what is the stationary phase? So let's say that I have an integral that has amplitude and a phase term. Okay. So here, if we assume that your frequency is high, then this particular term, a to the power I omega phi, will oscillate rapidly except for some points here. And those are the stationary paths. Everything else cancels out. And those stationary paths are what gives you reflections here. So if you just take one flat layer and I say I have a source here, I have a receiver here, and we all assume that reflection is coming from the midpoint, right? But the waves are everywhere. So why can't we get something from here or from here? The thing is that they are all present, but the most prominent or the most important is this path that gives you this. So if you look at this particular integral and then do a stationary phase, what you see is that that gives you Snell's law. Sine theta 1 equals sine theta 2, and that is the point corresponding to the stationary phase. Okay. Okay, so this is one approach that has been used quite commonly. One other approach that has been talked about is Born formulation, and that's what I'm going to talk about next. So in Kirchhoff method, we are defining the interfaces. Okay, and then we can trace rays, and then we can calculate travel time, and we can calculate the Green's function that gives us this reflection. The Born approximation, what we are assuming is that there's a background. So I have the velocity model. This velocity model is a function of, say, x and z. So I can say that I have a background, okay, plus a perturbation. Now this background can be homogeneous, or it could be just depth dependent, or it could even be x and z dependent. There's no restrictions on that. So you take the difference of these two. So that means here, if I assume that my background is homogeneous, so these are all the scatterers that I have in this medium. In fact, in one of the papers with Ranjit Shah, we showed that this actually reduces to the Kirchhoff integral for the homogeneous and flat layer reflection. So in any case, so this is the model that we're going to now talk about. Okay, let's see how this works out. So this is our pressure wave field, and this is in the frequency domain. So I have this time domain and offset domain pressure wave field, and this is my Fourier transform, and I get my famous Helmholtz equation, which looks like this. Okay, and k equals omega over c. This is the spatially varying wave number, and this is velocity, right? So what we do here is just a second. Yeah. So what we do here is we say that I define a potential, scattering potential, which is the difference between k squared minus k naught squared. This is my background wave number. That uses a background velocity c naught. Okay. So here, if you look at this equation for the background, I can say that, so I can take this original equation, which is what I have here. So what I have is del square plus k squared p, right? So here I can get k K squared is basically K0 squared plus P squared, right? So so this K squared, I can put this K naught squared times this. And it turns out, and that's equal to V, it turns out that I can write my background solution of P when I have this term. So essentially, this perturbation is causing an extra term as the source term. Okay? This is your original source, and this came out because you're assuming that your medium is a background and a perturbation to it. And that comes from here. Okay? Now, what does it do to our formulation? So first of all, let's write down the Green's function for the background medium. Okay? So if the background is homogeneous, then I have a closed form solution for the Green's function. And this is something that we have derived in the class, right? So I know what this is. In 3D and in 2D, we have a Hankel function. Now, if I look at this equation now, so remember, please pay attention to this. What is this equation telling you? Is that this is my extra source term, right? So if I take the Green's function and I actually convolve it with my source function, extra source function, I can get the wave field P, right? This is for the background. Now, the problem with this formulation is that in the right hand side, I have the full Green's function for the actual medium, which we don't know. So here, what I have is in this integral, I have this P on the right hand side, and this is what we're trying to solve, right? So this is a nonlinear integral equation. So, and this is our incident wave field, which is simple. That is, so there were two terms there, right? One was the SX term, one was this term. So this is your incident field. So like I said before, the solution really is in a situation which we call catch-22, because you want to solve for P, but that P has to be known to be able to solve P. So it defeats the purpose. And this is where we use theory from quantum mechanics. So this is the Lippmann-Schwinger equation from quantum mechanics. So what we do is first we write this in this operator notation. So this T hat fx is nothing but this integral here. It's the convolution integral. Okay? So your P is the incident P plus T hat P, right? So now I can say that I can take this. So P is equal to your P incident plus T hat P, right? So now I can take this to the right hand side. So then I have P, and then I have, these are all, you can write this in matrices, minus T hat is equal to, or I minus T hat P is equal to P incidence. So you can say that P is equal to P incident. P equals your P incident I minus T hat. Okay. But remember, the T hat actually also has P in it. So the way we'll then do this is I can just expand this as a series, because this is to the power minus 1. We expand this as a series, and you can say that I have P incident, T hat P incident, T square P incidence, T to the power 3 P incidence. And this is called a bond series. So what is done here is we say that this G naught F which I started off earlier, is G naught, which is basically background Green's function, and that approximates my V. So what we say is that to solve this equation, which requires that we know P, we will first assume that P is the same as G naught. Okay. And then that will have some error. And then I will use the new part term. And then I add it to the second term. And I will keep on adding the perturbation each time. Okay. And then I go from there. And this formulation gives you something that looks like this. So your zeroth order perturbation. So this will have no scattering. And then firstborn will take this. So this will take this P and put it in here. And then it will take the next one with third, second order scattering and so on. So then in general, we have n terms, which gives you n-fold scattering. So this is kind of nice to relate to our reflectivity method. But we're talking about internal multiples and things like that. So here, what I'm talking about is that we have scatterers. Okay. So this could be one interaction, and then you can have multiple interactions and things like that. And those are given by higher and higher order terms. And this is the full bond series, but this is still approximate because we assumed that my velocity field is, or rather it was like 1 over velocity is equal to 1 over background plus 1 over say perturbation. Okay, so slowness was basically, or rather I'll put the slowness is equal to S naught plus delta S. So here also we assume that delta S over S is far, far less than 1. And that is why we can truncate terms of higher order. And this formulation is actually quite unstable if you go to higher order terms, and if your background is quite far from the true model. And this is the kind of theory that this inversion method that uh, Ashok was talking about that makes use of. So it uses Green's functions for the background, medium, and perturb. So the trick for this to be able to work is that your background should not be very far from the true velocity. Okay. So then frequency domain, you can simply write it like this, that P equals P incident. And this is all, convolution integrals. So G, V, and P. So you can write this as G naught B, G naught V, 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 and so on. So this G naught is the background and V is your perturbation or scattering potential. So once you know the background, you can use this series to compute the full response. Okay. So Ashok, is this clear?
Yes, sir, this is clear. So one question arises that in Kennett it was very easy to expand to anisotropy or to put attenuation into it.
Yeah.
So is it also this
Yeah.
case
Yeah.
for this bond?
Yeah. Yes. Yes. You can do that for anisotropic case. In fact, the paper I was mentioning to you that I wrote with Shaw, there we actually treated the full anisotropic medium. So
Okay.
yeah. Okay. Yeah, this can be extended to anisotropic media as well. The Green's function have to be calculated for the background anisotropic medium. You can actually use isotropic medium also as a background, but I don't know how well that will work. Okay. Okay.
Yes.
So any other question? That's a very good question. Any other question?
So
Okay.
when we do,
Yeah.
yeah. So one question, sir. So
Yeah.
when we do our finite difference update on the gradient, then we try to create calculate the adjoint.
Yeah.
So we treat. Is it the same thing when you calculate the residuals at the receivers and treat it as source? So we are
Yes.
actually. Is it the same green function over there?
So it's a little different because what we do there is, so the residual in the data is treated as your source. Okay.
Yeah.
residual in the data is treated as the source. It's not the residual, and perturbation is not in the velocity, but in the data. And we use that. But in some sense, it's the same because, after all, you're using the residual to compute the residual in velocity using a joint method. So it goes backward rather than forward.
Okay.
Yeah. Anything else on this? Go to the next slide. So the convergence condition is that this should be less than or equal to 1. And if that is violated, then it does not work very well. So, yeah, so this is the classical series. And now I'm going to talk about a method which actually uh, is valid for when it converges for. If you see that if you run bond series for a realistic model like Marmousi and other things, even for two-layer case, you'll see that after some iterations, it diverges if the background is far from the true. But it turns out that there is a method that proposes a convergent bond series. So what they do here is that they use a small perturbation in potential, which is imaginary. Okay, and what they're saying is that we can take the difference and then come up with some number. Depending on that, we can choose this epsilon, but theoretically, calculated epsilon is not that good, we have found, but it can be done by trial and error. So the claim here is that if you make this correction, then on the left hand side, we have this. And since we have this term in both left hand and right hand side, I think this basically, since it is in V here, uh, cancels out, so we have the same wave equation. Now, if you did that, then if you take it like this, so what it turns out that your Gin's function would look like this. And we have this I epsilon. And this is actually your damping term. Okay. So this shift makes the background medium lossy. Okay. And the corresponding Green's function in 3 dimensions that becomes this. So this is like adding attenuation in the background medium. And if you did that, then your series actually does converge. Okay. So that what that does, it localizes the total energy, and that becomes finite, and which is the mechanism that it converges. So then scattering potential precisely compensates the loss. And so this claim, I'm not sure. Numerically, we're seeing some differences in the solution, but now this is a pretty decent paper in electrical engineering that we are working on. I'll show you some example. So what is done here is that this is essentially working as a preconditioner, and that modifies our Lippmann-Schwinger equation. And then we have a solution that looks like this. And now you have a series. This is the modified bond series, and that has all of these terms. The only thing that's different is the addition of I epsilon in the potential. And that does the trick. Okay. This is basically the modification of those equations here. So let me show you some figures that my student calculated. Like I told you earlier, this is something that we're working on now. Are you seeing the screen?
Yes, sir.
So this shows you real and imaginary part. And what you see is for a two-layer case, and you can see that after some time, it's actually getting garbage. It should look like all circular all the way. Now let's see, what is this? Yeah, so if you go to much higher number of terms, you can see that at 15 hertz, particularly high frequency, you can see how it actually becomes unstable. Now, if I go to the same series, this is 10 hertz. This is my corrected bond series. You see there is some damping effect at the bottom, but otherwise the series does converge. This is for a single frequency, and this shows you at go to a higher frequency. There was 10 hertz, and this is 15 hertz, and this is you can see the interface where the transmission is taking place. So this convergent bond series actually does work. And then I don't have the movie, but this is basically our Marmusi model. And this is the real part. And you can actually see that it actually did a good job. This is for 10 hertz, and this is for 15 hertz. So even for complex velocity model, this seems to be converging and giving us reasonably good results.
So, sir,
But yeah,
attenuation is taken care of in the convergent bond series itself when you talk
yeah,
about
but
damping.
yeah, so it actually adds something which is kind of artificial. We're saying that, but the real medium does have attenuation. So I think it's a but the number that is used here is sort of like a cosmetic. It's not a real physical parameter. Just to bring in stability. So we are also working. This is more of a research topic right now. So we are also working on further understanding of the theory behind this. So
So if we compare, sir, Kennett versus this bond method, so in Kennett we have, I mean, every
yeah,
physics is taken care of, whether it is
right,
attenuation or anisotropy. But
right.
unlike here the attenuation is somewhat hidden inside the maths.
Yeah, and attenuation is a sort of not the true attenuation. It's more of a, sort of, it's more of a cosmetic, like I said before. Okay.
And
So yeah,
about the
this
inversion, sir. Yes. Go ahead, sir.
now the inversion of this I have not talked about today. We'll probably do it next time. But
Okay.
yeah, so I just wanted to just go about the theory. But
Okay.
the inversion using this modified bond series has not been reported anywhere. So we have
Okay.
that is something we're working on. So,
Okay, is it not in the paper I shared with you, sir, the PhD thesis by Peter Haffinger?
but that's not the convergent bond series that I'm
Okay.
talking about today. So they use the
Okay.
bond series, but what they each time made sure that their background is not very far from the true model.
Okay.
Okay.
So their inversion is simply gradient descent, and they are not using global inversion. So it seems their starting model, what you say, is very close to the true model.
Not only that, if you use this series representation, you need to have that. Okay.
Okay.
But I will go over it in more details next week.
Okay.
So here
Yeah.
I was showing you some traces, and you can see that bond series does not match very good with the finite difference, but convergent bond series actually matches better. So yeah, so the difference is that Kirchhoff evaluation is by method of stationary phase gives you Zoprates, and evaluation by the method of stationary phase here gives you linearized reflection coefficient for bond. So bond, we used only I think the first order term in bond to show that, but maybe for higher order term it will give you exact Zoprates equation, but we haven't proved it yet. Okay, and these are some references. Um, I think that's all I planned for today. So let's have some discussion because I was hoping we can have some time for discussion also. If anybody has any
Then I
doubt
have
on this.
Yeah, one I have one confusion. When you say when you are formulating Kennett,
Hmm.
but it is in terms of reflection coefficients.
Yeah,
But these reflection coefficients are actually Jopre's are getting from Jopre's. Is it
yeah, yeah,
okay? So
yeah.
we have to use Jopre's as well as the Kennett formulation to get the exact synthetic cycle.
Right, because Kenneth will give you all the reverberations.
Okay, okay,
Yeah.
okay, got it.
And it's not a convolution model as such because you are doing everything in P omega domain and then transforming it. And you're
Okay,
including all the reverberations here.
yeah,
So we have a similar series in the Born also, but it's like I showed you, it's approximate, right? For
okay,
laterally varying media. If you have a lot of terms, it converges to the true solution, but otherwise it's approximate.
okay.
So did you get any feedback from other students on the assignment I gave you last time? Or?
I think the students are they have done some NMO equations and calculated angle gather. I saw one student have done it. They showed me some images. They are not here. I think
Okay.
maybe they are sitting together. But I
I
saw
think
some
I think they are
assignments.
there, Ashok. They are all
Okay,
joining together from one
together.
laptop.
Okay, yeah.
So why don't you tell them to
So
show what they have?
okay, I will tell them next. Yeah, yeah. Please go ahead.
Are they working in your office or?
They are in our office, sir, but they are at different site.
Yeah.
Few are with us, and few are at Sahadol, our CVM site office. So it's slightly difficult to interact, but I have seen their results. They have showed it in WhatsApp. Next time, I will
Okay.
tell them to present to you, sir.
Okay. Yeah, that'll be good. Yeah. Okay. So if you have any question on the previous lectures,
Sir,
also we
I have
can.
one question on FWI, which I want. Can I ask now, sir, or
Yeah. Yeah. Go ahead.
will so, sir, I have some confusion about the norm, what we use normally. Let's say if
Yes.
you are starting with a deep water data, then I started with the L2 norm,
Yes.
and I could not get a, I mean, good result. But when I moved to the phase-based norm, then I got some result which was geologically possible. So is it? I mean, I don't know. I'm new to this inversion. So how should we start? What kind of norm should we start with? Let's say if you're going for a 3 to 5 purge inversion and you want to avoid the cycle skipping, then should we start with the phase first and then move
Yeah, I think
to?
it's always a good idea to start with the phase part because other thing is that your amplitude in the real data is not all that reliable, right? It's not reliable because they don't exactly follow the physics of all the assumptions we have in the physics of wave propagation. So in the phase time, if you're just focusing on the phase, then it's basically matching the travel time, but including all possible paths. So that is much better. The medium may have, you're talking about real data inversion, right?
Yeah, yes, sir. Yeah, real data. Yeah.
Yeah, yeah.
And when do we move to L2? When is it required in higher
No,
frequencies,
no,
or
it's not
I should stick with?
necessary. It's not necessary.
Okay,
Yeah.
okay. Even with the
But
elastic case, sir?
maybe I will have some lecture on inversion. I'll talk about different norms also.
Okay,
Okay.
okay, okay, great.
So then you can see L1 norm is there, L2 is there, and then
Okay. So I have some results, sir. Maybe next
yeah.
week I will share with you and have your comments so that how we can improve it further. I'm
Yeah,
using
yeah, that'll be
Devito.
great. Yeah. Yeah, that'll be great. Yes. Okay. Okay, so if there is no other question, then I should probably call it a day and then we can follow up from there. I will send you the PowerPoints and also I have written some notes for you guys, so I can send those to you.
Yeah, and also sir references, some books reference
Yeah, yeah, yeah.
for
So the
students. Yeah.
references will be in those documents that I
Okay.
sent you. Yeah.
And the assignment for today's assignment would be the Kenneth equation, preparing
Yeah,
synthetic?
yeah, yeah.
Okay,
So,
okay, sir.
yeah, I was going to say that if anybody wants to do this for acoustic case, that is simplest. Okay.
Okay,
So, let me tell you what you can do is just write a code, and I already gave you the algorithm, right? Loop over P, loop over frequency, loop over layers, and then just do acoustic case where reflection coefficient is scalar and transmission coefficient scalar. So you don't have to the RDTD, RUTU, these are not matrices anymore, but you can still use the Kennett equation. So you can find if you search, you can find the equation for the acoustic case also. But you can
yeah,
code it for if you want, you can code it for elastic case if you like.
okay,
That, that might be a bit time consuming, but depending on how much time you can give it to, I think you should try
okay,
to write a code. You should try to write a code. I was gonna say that. Yeah, for today, I think the assignment would be connect stuff. So
okay,
generate tau p and then xt. Okay.
okay, sir.
Anything else? No, I hope that others also work on the assignment. I think it's for their own benefit because otherwise, as they say, you don't learn it until you code it. So
Yeah, true, sir.
once you start to code, you realize how that you didn't really understand everything.
Yeah.
Then you have to go back. Okay, so any comment on how the lectures are going? Is it too like complex or is it understandable? Because I wanted to hear that too.
Yes, sir. The lectures are, I mean, partly it is understandable, but when there is more complex maths, then it is something, I mean, we are not able to understand, but at least the end result is understood well. And what we have to use it, that is well understood.
Yeah,
I
so
mean,
you need to work out some of these things, then you will understand yourself how it
right,
goes.
right, sure. Yeah. I mean, like Kirchhoff and Bohm, I was not aware that Kirchhoff and Bohm are very similar. We have been
Yeah,
using Kirchhoff migration for so long, but
yeah, yeah,
the real maths was not well understood. I mean, till
yeah,
you
yeah,
showed the examples.
yeah,
Uh, so this was something very good.
yeah. And Born, a lot of people are using now, so I think
Yeah.
it's a good idea. We're also writing an algorithm for doing this using machine learning, where it automatically figures out that epsilon term. So we'll see how
Okay.
that goes.
So, sir, this modified what you call convergent bond series.
Yeah,
So, are you also working on an inversion based on this series? Is what the Helios
yes,
does? So that
yeah,
would be
yeah.
better than what Helios does.
I don't know, but we'll see. I hope that it
Yeah.
is. Yeah,
Yeah. Okay.
yeah.
So we have that software, Helios, in our office, and I have
Okay,
done some inversion using that.
okay.
So they basically work in the lambda and mu domain, compressibility, compliance, and all
And
those.
that's for laterally varying media, right? For heterogeneous media, right?
Yeah. And they also start with a model, a low
Okay.
frequency model, and but they used only a gradient descent.
Yeah,
Unlike
yeah,
the unlike the Kennett formulation, they start with a I mean global inversion like genetic algorithm and all those, but they are using just a gradient descent, and they have a term for higher order scattering. What you talked today, like
yeah,
first
yeah,
order, second order, third
yeah,
order.
yeah,
Some maximum it goes up to seventh order. They say
yeah.
that beyond seventh order, I mean, if there is no point. Maybe
Yeah.
because the way those wave fields are becoming non-circular and becoming unstable.
Maybe they have also included some kind of damping there. I don't know. I'll have to look into that.
Okay, maybe so. I think damping is there because I asked the question because what if I want an attenuation from your result? They were giving compliance, compressibility, but they were silent on attenuation. So when I asked them, they could not answer satisfactorily. Maybe because of the maths involved.
Yeah, I think we have some other ideas to. Essentially, the student's PhD will be on that, and then we're looking into some other aspects by building in, machine learning and things like that into this.
So how is machine learning getting into it, sir? I mean, can you throw some light on it?
Yeah, so all of these series terms. So we have different terms. So what we can do is we can calculate the Green's function, and then we have the machine learning term, machine learning, and then we can whatever we get, we just put it back. This is called recurrent neural network. So
Okay,
whatever,
RNN.
yeah. So it basically feeds back a feedback neural network, and then then we just repeat it until it converges to the trial solution. So we can put in finite difference Green's functions as the truth, and then converge it. So what happens is that in that case, once it has converged, then we have the trained network. So it will quickly give you the full wave field without solving the finite
Okay,
differences.
okay, so it will be faster. Yeah.
Hope that works. This is still in the idea stage. So student is working on that.
Okay,
Yeah.
great, sir.
Yeah. So are you coming to the image conference, or anybody coming to the image conference?
I think somebody from Reliance will go, but Santosh, you are not. Are you going to the image?
No, no, I think he is mentioning about image, not the EAG one. EAG one, nobody's
Okay,
image is still not
okay,
decided, so nobody has as of now.
Yeah.
okay, okay.
Yeah, EAG, I didn't go because it's well in this week is happening next this coming week. Yeah.
Yeah, yeah, this week. Yeah, coming week. Yeah,
Yeah. Okay then.
yeah. Okay, sir. Thank
Okay.
you very much.
Thank you, sir.
Thank you.